Okay, today we're going to implement the joypad because we had a hack for that when we were working on the PPU. The hack was that we just needed some data to be in the joypad registers so that Tetris could actually proceed in loading. It was doing some checks for some specific byte. To get that working, we had to just implement a placeholder value. So today, let's just do it right. And so I've had Claude just tell me about the joypad, and so we can actually get just a quick overview here, and then we'll just get right onto it. So um, the hardware problem. So there's a register called FF00, which is going to be named JoyP register. So the hardware problem, the Game Boy has 8 buttons, but the joypad register is only 8 bits wide. So you can kind of understand that 1 bit corresponds to one of the buttons. The designers solved this by splitting the buttons into 2 groups and using a multiplexing scheme. The CPU selects which group to read by writing to the same register it reads from. So the 2 button groups. So you have the directional pad and the action stuff. So the directional pad, bit 4, tells you whether or not, I guess, the D-pad is going to be used. Bit 3 is down, bit 2 is up, bit 1 is left, bit 0 is right. So if any one of these are on, it tells you that the current button of when any one of these D-pad buttons are currently being pressed. And then action buttons, where bit 5 is a 0. If this is 0, then any one of these, bit 3, 2, 1, 0. If any one of these are on, it actually means that start, select, B, or A are on. So this is like kind of like the mode here. So bits 7 and bit 6 are unused. So reads are just going to be 1, probably hard coded. And then bit 5 is just select action buttons. So 0 selected. So active low. Okay, so 0 means kind of true here in this case. D-pad, 0. Okay, so these 2. And then any one of these, when they're 0, it means that they're being pressed. Okay, so everything is active low. A 0-bit means selected or pressed. 1 means not selected or not pressed. This is counterintuitive, but reflects the hardware pull-ups resistors. So how games read input. Games use a 2-step process. First, to read the D-pad, bit 5. Okay, so think, so read 20, so hex 20, so it's going to be 0000. Let me just pull this up. So hex is, in this case, 20. Let's see. Stroke width too big. This one. How about this one? Okay, there we go. So hex 20 means it's 0, 0, 0, 0, and then 0, 0, 1, 0. Ugh. Okay, so 0, but 0, 1, 2, 3, 4, 5 right there. So that makes sense. If this is 1, this is going to be deselect action. Bit 4 equals 0, select D-pad. So write to P1 register. Okay, so at LDH, so LDH is the H register is what? What is the H register starting at? FF00, is that what it is? So let's ask. Just on the other side, multitasking. What is H register in Game Boy? I keep forgetting this. So the high side of the 16-bit HR register pair. So in this case, the whatever value is in address of 00. So load A into that part. Okay. So what about so LDH00A is high page store instruction. It writes A into IO high RAM so at address F0xFF00 plus N, where N is the 8-bit immediate. So with 0, so this is the offset, right? So LDH always starts at here, apparently. So if LDH always starts at 0xFF00, doing an LDH 00 just gives that an offset of 00, which is exactly actually the joypad register where that starts out with. So that means anything that the value of A is going to be written to here, right? So in this case, 20, hex 20 is going to be written to the joypad register, and then we're going to read that back in to A, and then at this part here, we're going to actually read the first 4 bits to tell us which directional button is going to be not directional, sorry, which action button is going to be pressed. So yeah, in this case here, let's see here, some mass lower nibble, and then here's the read action buttons. In this case, bit 5 is going to be 0, so it's going to be 10 in this case. 10. Yeah, because bit 4 is going to be active, bit 5 is going to be inactive. It's really confusing. It's like backwards. So games typically read both groups of each frame and combine them into a full 8-button state. Okay, so we had to do these 2 parts all the time. Okay. What happens when neither or both groups are selected? So if bits 5 and 400 mean both selected, bits 0 to 3 reflect OR of both groups. If any matching button is pressed, bit equals to 0. Games rarely do this. 1-1, neither selected. Bits 0 to 3 all read 1, no buttons. This is the idle state. That makes sense. So bits 5 and 4, when they're both 1-1, that means bits 0 to 3 should read all 1. Okay. Okay, so the joypad interrupt if if bit 4. When any button goes from not pressed to pressed, bit transitions from 1 to 0, again backwards, the hardware can fire a joypad interrupt. This is mainly used for one thing: waking from stop mode. The Game Boy enters stop or deep sleep to save battery, and a button press wakes it up. In practice, most games don't enable the joypad interrupt. They just poll 0xFF00 every frame during V-blank. Pokemon polls rather than using the interrupt. Why the hack returns 0xCF? Our current hack returns 0xCF, which is 1100. So this means, right here, these two means both are selected, right? But all of this is not pressed. So right here, so both groups are selected, but no buttons pressed. Without this, the register returned 0x00, which games interpret as all buttons pressed simultaneously, causing touchers to immediately react to phantom input. Summary: the joypad is electrically simple. It's just a matrix of switches with select lines. The complexity is in the software protocol. Write to a select group, read to the button state. Everything is inverted. The implementation needs to track 8 independent button states and respond correctly based on which select line the game has activated. So in this case, what's hard is not for us, the emulator side of things, but it's actually the game programmers that had to remember all these little details about like that inversion and how to like manipulate the bits, and you had to like read both the D-pad and action group buttons at the same, like not at the same time, but like consecutively to actually figure out all of the 8 button states. For us, we're just going to have to emulate the functionality, the things that the game developers actually need. So let's build the joypad class then. Let's build the joypad class and then implement it. Write test 2. Follow all patterns we have been doing in this project. Okay, Yeah. Okay. Um, we'll just let that go. For some reason, I don't know. Claude's been a little slow today. Took me a while to get all this information for whatever reason. But yeah. Okay. So again, this is auto accept edits. We don't want to clear the context. Um, so let's just go for that. So basically what it's going to do, it's just going to create this simple joypad class. Again, memory mapped.io, right? So we had to basically reroute the address to the 0x ff00 address. And then from here, we just do a bunch of bitwise operations here to select either the D-pad or the action. Remember, this one's bit 4, this one's bit 5. And then we'll see what the result really is when we combine them. And then this is the last 4 bits from 0 to bit 3. And yeah, so then we write the value here. So 0x30 just ensures that 4 and 5 are the ones that are actually changed. So the select bits, right? So it's going to be 0, 0, 1, 1 on the high nibble, okay? And then press is just pseudocode here for here. But anyway, so this is what it's going to do. It's going to change GB memory, again, to the memory map.io. Then we're going to initialize a joypad in the Game Boy, which makes sense. Then we're going to write a bunch of tests, and that's about it. Okay, so we did all that. It's wiring now, but we can actually see some of the changes in here. So yeah, it's going to create the joypad class, joypad here. The button mapping, again, right, left, up, down, 0, 1, 2, 3, A, B, select start, 0, 1, 2, 3, and that's just telling us the bit positions. So we'll have select, which is going to be 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0. So that's 0x30. Then 0x0f is going to be D-pad, 0x0f is going to be buttons, so the lower nibbles. And then memory, so this is going to come from all the other, like Game Boy, CPU, and all that stuff. And then read address. This is unused, so I don't know. Same thing here. There's just asked later on, but yeah, everything else looks about what we learned, right? So press is going to turn that to 0, turn that specific lower nibble bit to 0. In this case, we're going to find, so the button here is going to be, let's say, left. So it's going to find the button map left, and that's going to be D-pad 1. So it's going to look for D-pad. So was released. Basically, we want to see if by applying the mask here, okay, so that's 0010. Is that it? 00, no, bit is going to be, yeah, 0010, because we're going to shift 1 bit here. 0010 is going to, when we mask that with the current D-pad, is that a 1 or a non-zero? If so, then yeah, it was idle. It was not pressed. So then now we just have to not that, so it'll be 1101, and we're going to AND it with whatever we had here. We're going to take that, and we're going to AND it with the current D-pad. Okay, so same thing here for the action buttons, and then we're just going to request a joypad interrupt. Yeah, and then release just does everything the other way around. So press release. Okay. Yeah. So that's about it. Oh yeah, we should see if we remove the hack or not. Do we need to remove the hack? Do we need to remove the hack? Yeah. So we removed the hack, and let's see if we can still run Tetris. So let's see if we can still render something to the render Tetris, and then we can tell it to run Tetris. Was it run Tetris.py? So it's going to try to run Tetris.py. It's going to see whether or not it can see the ASCII frame buffer, and if so, we're in good shape. What we want to do now then is we need to rendering perfectly. Okay, so logo menu and copyright all intact. The joypad replacement is fully working. Okay, commit and push this, update agents.md, and then the design.md with a detailed overview on how the joypad works. And I think since the code is relatively easy to understand, we don't need to do a code overview. No need to do a code walkthrough. Okay, so we'll have it do that for a bit. And I think the next step is to actually create some sort of like a UI, so that we can actually see on screen and actually move our joypad. And then see things update per frame, maybe. Or we can implement all the other MVCs. So MVC 2 and 3. We could do that. So let's think about it. Let's consult afterwards. Okay, so next steps, I wanted to create a simple GUI, but I gave it a choice, simple GUI or implement more MVCs. Claude says a GUI with joypad input is the clear next step. They naturally go together and give you the biggest payoff. Right now, you have a frame buffer with no real-time display and a joypad input with joypad with no input source. A GUI solves both at once and lets you actually play Tetris. My suggested order, so first we're going to do GUI plus joypad input. We're just going to do this together. Use something like Pygame or Piglet. Map keyboard keys to joypad press release. Render the PPU frame buffer each frame. This turns the emulator from dump ASCII and exit into an interactive playable emulator. More MVCs after GUI. Tetris is MVC 0, so the GUI gives immediate results with what you have, but Pokemon Red Blue needs MVC 3 with RTC, so real-time clock, so you need to tackle that next when you're ready to move beyond Tetris. Debugging MVC's issues is also much easier when you have a live display, so want to start on the GUI plus input. Yeah. So I asked, okay, well, consider that we also want to implement an HTML version that can send post requests to also send input. So we had to make this pretty modular. What is the difference between Pygame and Piglet? Which one will be more simple to do? So Pygame versus Piglet. Pygame is a wraparound SDL2, huge community, tons of tutorials, requires pygame.init, event loop, and surface splitting. Simple but slightly more boilerplate, very battle tested for emulators. Piglet, pure Python, no dependencies beyond OpenGL. Cleaner API, window event decorators, but smaller community. Can feel more Pythonic, but OpenGL can be overkill for 2D pixel rendering. For this project, Pygame. It's simple for pixel level frame buffer rendering, which is exactly what we need. Has straightforward keyboard event handling and is also more common choice for emulator front ends. On modularity for HTML front end, the key is keeping the GUI as a thin layer. The architecture should be source front end base.py, Pygame front end .py, and then later HTML5 REST front end is a separate consumer of the same interface. So the Pygame front end and future HTML5 front end are just both receive frame buffer data, display, receive input events, call joypad, press, release. The emulator core doesn't know or care which front end is attached. The HTML version will post button presses to a REST API, that calls the same joypad press release methods. Want me to plan this out? Yes, plan it out, but yeah, just don't worry too much about the project structure as it is. Uh, Actually, no. Yeah, let's plan it out. Let's plan it out, and then can you show me how you will actually make it so that the emulator actually runs at the, was it around 4 megahertz clock? Are we actually, I'm using actually a lot, but like, are we going to execute let's say 4 million or so cycles within 1 second? And if we, let's say, don't, if we are faster, we just sleep for the remaining period. So what I'm saying is that your emulator has to run at a specific speed, right? Like you have to render at a specific speed, you have to calculate a specific pace, whatever. But basically, our computers, like our desktop computer, is very, very fast. And so we could end up doing like maybe like 5 seconds worth of Game Boy within like a second, for example. That would be like, I don't know, 20 million cycles emulated. So the plan, or at least in general from emulator development, you kind of want to stick within the budget of certain cycles per second, which is what the, a CPU would do for the Game Boy, right? So the Game Boy CPU in this case, the Game Boy CPU was about 4.19 megahertz, so about 4.2 million cycles for 1 second. So we actually had to try and attempt to emulate that exactly, execute 4.2 million cycles in 1 second. Now, I think, in general, if you actually end up doing 4.2 million cycles in a second before a second completes, you would just generally sleep for the rest of it or do something busy to kind of eat up that time. Yeah, so what's the plan here? What does that loop actually look like? So we'll let COD plan and maybe it'll address that question. But in general, if this is 4.2 megahertz, we had to be sticking to that specification per second. A way to do that is, since we're already returning cycles every single time we run an instruction, as soon as we hit around 4.2 million, we're just going to sleep for the rest of the time. And I'm being very optimistic that my 9800X3D can actually do way more than that for this emulator. But at the same time, we're doing this in Python, which is generally pretty slow. So let's see. And also it's unoptimized, right? Like this is just a very basic emulator, so not even sure if how this is gonna turn out. And this already is gonna be, it's gonna be 100k tokens just on its own, just trying to explore, because we had compacted the conversation earlier. So now it has to kind of gain some context on some of the code here. Yeah. Okay, so it's planning. I don't know what it means, but let me verify the register concern the plan agent raised about run tetris.py. I think one of the subagents, Claude spawned, is misinterpreting something, but I think one of the other agents corrected it. Okay, so writing up the final plan, it's chewing up tokens. All right, so we have a very interesting plan here. Let's read it. Okay, so the emulator has a working CPU, PPU, timer, serial, joypad, and MP0 cartridge. Yay! So timing strategy. Basically my question, right, about the 4.2 million cycles. So the Game Boy runs at 4.2 million hertz. One frame equals 154 scan lines times 156 dots, which is going to be about 70k T cycles. So in this case, you're going to have to render about 70k cycles in about 16 milliseconds to achieve about 60 frames per second. So the main loop is while running, frame start, time.perf counter, handle input events, target, is going to be the current cycles plus cycles per frame. It's going to be 70K. So we're going to run for this many times to render that single frame. We're going to render the frame buffer because at this point we're going to handle input events. It's going to set all the joypad registers already before we're going to run for this many amount of cycles. Then we're going to render the frame buffer to the Pygame window. And then we're going to take the current time minus the frame start. So how many times has it lapsed since then? And then whatever's remaining, we're going to sleep. So this is exactly what I said. So if remaining is less than 0, the frame took too long, we're going to skip sleep, and we're going to just go and run again. And this is going to create a very laggy emulator if you're in this situation. So the CPU's run max cycles uses current cycles as an absolute monotonic counter. It exits when current cycles is greater than equals max cycles. Each frame, we advance the target by 70K cycles. The CPU may overshoot by one instruction, basically 4 to 16 cycles, which is fine. The next frame's target accounts for it automatically since we always read current cycles fresh. Sure. Okay, so Pygame front end, we're going to have the Pygame window, surface, and event loop initialized here. Game Boy instance will be passed in. So run is going to be calling the Game Boy run loop. And then we're going to handle events here. So this is going to be, all this right here is going to be most likely this stuff here. Okay, cycles per frame. So that's a constant, 70K. Frame duration, we need about 16.74 milliseconds. And then DMG palette, this is just the green palette. And then rendering, okay, so for rendering, oh, here is the keys. So I have a split keyboard, so arrow keys aren't going to fly for me. I'm going to have to say, okay, well, instead of using arrow keys, use WASD. And then I'm not a fan of Z and X because again I have a split keyboard, so I'm gonna say J and K, and then start would be enter is fine. Select will be delete. Escape will be okay. Will be quit. Okay, that's fine. Yeah, so then this will be a 160 by 144 surface. Transform scales to the window size, simple and correct. If rendering becomes a bottleneck, optimize later. Sure. Okay, so now we're going to do scale of 4. That's fine. So that'll be like 400 by, or 500 by 400 something. Sure, all this is test. Okay. Yeah, that's fine. Okay, now type here to tell what caught change. Okay, auto. No, not auto. We need to change the directional keys from arrow to WASD. Also, select should be delete key on the keyboard. And then I think that's pretty much it. So we'll have it adjust that. Update that plan. Okay, so let's see. WASD, enter delete. Oh, also, was it BA, right? So A, B. I'm actually more of like a BA person. So J should be B, K should be A. Yeah, I'm more of that type. So I think even in the Game Boy itself, I have a Game Boy Advance, might be the same right here. So right there. So B is actually first, and then A is second. So okay, in this case here, that looks more correct. Yeah. Okay. So let's auto accept edits and just have it finagle. Yeah. We are now put into this decision that we had to make to install Pygame. I forgot to create a virtual environment. Whatever. Let's do it. Okay. Okay, this is unit tests. That's fine. So no F support. Just use AF to set both A and F at once. It should have known that. Okay, so now it's always the test that makes it kind of just go bonkers. So we'll just have it work through all that. Okay, so the IF register is masked to 5 bits. The test expectation was wrong. Okay. Okay, now all 19 tests pass. Fine. Let's check the full suite. All tests pass. So let's run Tetris.py to just see if it still works. Hopefully, render something. Everything works. Let me mark the final task complete. Okay, so what do we have here? We have the run Pygame. That's cool. We also have GameboyAI, so that just initializes the register to the correct values at post boot. Okay. Let's see here, Pygame front end. This is basically the Pygame implementation, so quite simple. Basically, our key map here is what we specified, right? WASD, JK, return, delete, fine. Okay, so GB width should be like 160 and then 144. Surface is going to be, okay, so it's going to be that size. And this is the exact same loop, and then we'll sleep for some duration until we quit. And then this just handles the key events. So for every single event, if it's a quit event, so we're just going to set self-running false. I think that's Control C. So if it's a key down, if it's escape, whatever. Otherwise, we're just going to do joypad.press the button. Okay. And then let's see here. So joypad.press. So Game Boy joypad. Well, at least here, joypad. 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 So joypad.press is going to take that button. Button is again referenced all the way here. So we're just going to pass in the Pygame front end the button. It's going to be keymap.get event.key. So key map here will just map to these, which you can just pass in directly to the joypad, and then we just render the frame. Okay, so we're using Blitz, so we're just gonna push pixels onto the screen. It looks like it'll work, I guess. So yeah, let's just run it. So Python run pygame whatever here. Okay, that was from last time. Let's do it. Yay! It works. That's so cool. Okay, so let's try it. Let's go one player. Okay, so we'll hit enter. Okay, so we have, what is it? It's game type A, music type. We have no music yet, but we'll do level. And look at this. Okay, so now let's take a look at our CPU, see if it's crazy. Because I think we're using CPU rendering. But yeah, this is a Game Boy emulator, right? So we've been working. So we've been working pretty hard on this. We finally got some game working. And yeah, the green feel. That's kind of like how a Game Boy looks like. I'm not gonna even like do the scan line filtering. I don't even know if there's scan lines on the LCD. I think there is, but yeah. Everything looks okay. I still don't understand. There's something wrong with my computer. Like really, like I think this Windows install needs to just be wiped because I for some reason only 1, 2, 3, 4, 5, 6. Only like 6 threads are being used. Is that just like a whistle thing, or let me just? I'm like having trouble. It's like 16 processors are logically okay. Whatever. I'll just eventually just go full on Linux on this thing. It's just that I want to finish this programming the Game Boy emulator so that we can start doing some the related reinforcement learning with Pokemon. But yeah, so here is basically the emulator, and I think this is also resizable and scalable too. Maybe not, but we can just change it. So let's do this. Let's see if we can take in an argument of scale. So scale 3, let's do scale 4. So scale 4 would probably look better on camera, maybe. No, something is overriding it. Or maybe scale 4 is not big at all. Scale 8, it'll probably look ugly. Okay, this is... Wow. Run Pygame? Probably because it's our argsot scale. Okay, I can just do dash dash scale, and then let's just change this back to 3. So dash dash scale will be our arguments. So dash dash scale, let's do 4. There we go. That looks better. Cool. So yeah, this is Tetris. Hello. Tetris, hello. Boom. Yeah. I'm like enjoying this game now. We made an emulator. Okay, so right now we can only pay Tetris, but let's commit and push and see if we can get the NBCs working. And then we'll try to get sound working too. And then after that, I don't know what else we're gonna do. We're gonna do the server. And I think when we do the server, let's try to at least, do what we do best and try to use a local model, or we can just do that ourselves. Yeah. I'm not even like thinking, I'm just like dropping stuff. So, yeah, I don't think I can correct myself. I can correct this one. Yeah, there we go. Please? Okay. And then, maybe this, and then a line here, and we'll just slowly fix ourselves. Right, so we'll just slowly fix ourselves. Block. Okay, we're getting kind of lucky with decent blocks. Yeah, we're getting kind of lucky with decent blocks. Okay, I think it's also easy mode. Come on, cool. Okay, I'm not gonna make this video too long, just watching me doing a let's play on Tetris. But yeah, we have a game working, so that's cool. Yeah, I'll stop right here. I'm getting too into it. Okay, so what's next? Okay, so let's see. Great, it works. Update agents.md again, and design.md to discuss how the front end works and timing related things, right? And then commit and push afterwards. Great work. Okay. We'll have it do that, and then we'll think about the next steps. Okay. So that's that. Not sure if I should split into. Okay, that's that. It's already done all its updates to agents.md. It's gonna push everything up, and we've done about maybe 35 minutes of this, so I think we do have more time to just plow ahead. I think at this point, now that we have some sort of GUI, it makes sense to start implementing the MVCs. So in this case, I would like to compact, but just to double check, did it update things? So what we want to search for is Pygame. So yes, it did update its to-dos. So that's a good thing. Did it update anything else? It's fine. How about the progress? Yeah, let's see. Yeah, I don't think it did. Okay, whatever. So yeah, I'm gonna have it compact. Well, let's actually see the tokens status. There we go. So let's see stats. No, how do we visualize? There we go. Context. Okay. How much have we used? Oh, we have a lot. Wait. No, we don't. Okay, let's compact. Okay, this is gonna take a while. So, okie dokie. Moving on to NPCs. So again, let's just get a quick review on what these more complex NPCs are. So I prompted to just give me a huge explanation. I think it's worth just reading word for word since we're at a good place. Let's do it. Okay, so great question. Here's a plain English breakdown of Game Boy NBCs. So the problem NBCs solve, the Game Boy CPU can only see 30 kilobytes of ROM at a time from addresses 0000 to 7FFF. But games can be much larger. Pokemon Red is 1 megabyte. NBCs are chips on the cartridge that swap different 16 kilobytes chunks of ROM and sometimes RAM into the CPU's view. We know that. Think of it like a filing cabinet. You can only have one drawer open at a time, and the NBC is the mechanism that opens and closes drawers. The first 16 kilobytes is always bank 0. That second 16 kilobytes from 0x4000 to 0x7FFFF is a switchable bank. You write a bank number to a special address, which we know, and that tells us exactly which bank to choose from in the cartridge, or at least the NBC will know. The NBC swaps in that chunk of ROM. And to the Game Boy, it's pretty transparent. So we already have NBC 0, no banking, max 32 kilobyte, and NBC 1, up to 2 megabyte ROM, 32 kilobyte RAM. So here's what comes next. NBC 2, built-in RAM, nibble-sized, used by a few early games, Kirby's Pinball Land. NBC 2 is simpler and quirkier than NBC 1. Why? ROM banking, up to 16 banks, 256 kilobytes. Write to 0x2000 to 0x3FFFF to select a bank. Only the lower 4 bits matter, banks 0 to 15. That makes sense. Bank 0 maps to bank 1, same quirk as NBC 1. So remember, you choose bank 0, it's always going to be bank 1. Built-in RAM, NBC 2 has 512 bytes of RAM built into the NBC chip itself, not a separate RAM chip. Each byte only uses the lower 4 bits. The upper 4 bits is read as garbage or undefined. You get 512 by 4-bit values. Huh. So isn't that just 256 bytes? Interesting. Well, I guess usable, right? RAM enable quirk. To enable disable RAM, you write to 0x0 to 0x3f, but only if bit 8 of the address is 0. The address's upper byte must be even. If bit 8 is 1, it's a ROM bank selected instead. This is the weirdest part of NBC 2. I'm not sure if I understand that. If bit 8 is 1, but how's there bit 8? It's going from 0 to 7. Wait. Okay, it's a ROM bank select instead. This is the weirdest part of NBC 2. I guess bit 8 corresponds to 7. RAM address range 0x8000 to 0x A1FF, only 512 bytes. That's true. Mirror view read beyond, because that's right up here. No banking mode register, simpler than NBC 1. Okay, implementation difficult, easy, simpler than NBC 1 since there's no RAM banking or mode switching. The nibble only RAM and address bit 8 quirk are the only tricky parts. Sure. Okay, let's see here. The NBC3, the Pokemon controller with optional RTC, used by Pokemon Gold, Silver Crystal, Pokemon Red, Blue, some versions, many others. This is the one you'll need for Pokemon. MBC3 is cleaner than MBC1. Yes! No weird banking mode registers. Okay, ROM banking of 228 banks, 2 megabytes. That makes sense. So 16 kilobytes times 128 gives you about 2 megabytes, I guess. Write to 0x2000, 0x3FFF, 7 bits used. Okay, that's true. 7 bits, 2 to 7 gives you 128. Bank 0 maps to bank 1, same as MBC1 too. Bank 0 at 0x0000 to 0x3FFFF is always fixed. RAM banking. So this bank 0, the first bank of the 2 banks, is never going to be switched out, which is also kind of like the rest of them. So RAM banking up to 4 RAM banks, 32 kilobyte total, 8 kilobyte each. Write the bank number 0x00, 0x03 to 0x4000 to 5FFF. So 4 RAM banks, 8 kilobytes each. So it's going to switch to write the RAM bank number from 0 to 3, that makes sense, to one of these addresses. Oh, right, there were only like 3 wires on the MBCs, which is why the ranges are so big. Okay, I'm following. Okay, so RAM must be enabled first by writing 0x0A to this address space. Okay, so real-time clock. What makes MBC3 special? Some MBC3 cartridges have a crystal oscillator on the board that keeps time even when the Game Boy is off, powered by the cartridge battery. This is how Pokemon Gold Silver know what time of day it is, day-night cycles, daily events, etc. So how it works. Oh yeah, I forgot that Pokemon Gold and Silver are also Game Boy games. They're Game Boy Color. Okay, so seconds. Okay, so 5 registers. So what is a second? Minutes, hours, day, high, day low, day high. Okay. Oh, yeah, because it's 365 days, I guess. Okay. The clever trick: the RTC registers are accessed through the same RAM bank register. Sure. So it's like their own memory mapped I/O. If you write 0 to 3, you get the RAM banks. If you write 8 to C, the A000 to BFFFF window shows the RTC register instead of the RAM. So games switch between I want to read the RAM and I want to read the clock by writing different values to the same register. Cool. Latching. The RTC ticks continuously. So if you read seconds, then minutes, a few cycles later, the seconds might have rolled over and the values would be inconsistent. To prevent this, MBC has a latch mechanism. You write 0x00, then 0x01 to 0x6000 to 0x7FFF, and it freezes a snapshot of the current time into a readable registers. You read the frozen values, then latch again next time you need them. The actual clock keeps ticking in the background. Halt bit. So basically, when you're reading these values, you're actually reading a snapshot, and everything else just keeps moving in the background. So you have to, like, if you want to get an update of it, you have to read the snapshot again. So halt bit 6 of the day high register stops the clock. Games uses during save load to prevent time from advancing. Day overflow bit 7 of day high is set when the day counter passes 511. 9-bit counter wraps. The gamer is responsible for clearing this flag. For emulation, you don't need a real crystal, just use the host system clock. When the game latches, compute how much real time has passed since the last latch and update the RTC registers accordingly. Some emulators persist the RTC base time to the save file so the time advances even between play sessions. Okay. Battery, SRAM persistence. Battery in the cartridge type means that the cartridge has a coin cell battery. So it's like a CR2025 battery and it's soldered onto the cartridge. I know because I've opened one of these up to try and attempt to replace the save battery before, only to realize I didn't have a CR2025 battery. And that's when I just decided I'm going to order an EverDrive. Okay, so in the cartridge type means the cartridge has a coin cell battery that keeps the RAM powered when the Game Boy is off. This is how save game works. Your saved data lives in cartridge RAM, and the battery keeps it alive. For emulation, this means that when your game writes to a cartridge RAM and you shut down, you should save the RAM contents into a save file. When you boot up again, load it back. Without this, saves are lost when you close the emulator. Makes sense. Okay, MBC5, the modern standard, used by Pokemon Yellow, Pokemon Gold, Silver, some versions, most late Game Boy Color games. MBC5 is the most straightforward MBC. It drops all the quirks. Nice. So it just slowly gets better. ROM banking up to 512 banks, 8 megs, and uses a 9-bit bank number split across 2 registers. And I don't think I can't remember any SNES game actually growing that big. Anyway, well, to be fair, I think the Game Boy overall lived a longer life. Went all the way up to advanced, because I consider Game Boy Color to be Game Boy. So, right, lower 8 bits, okay, right 8-bit, or bit 8, the 9th bit to, okay, this range, bank 0 is not remapped to bank 1, unlike MBC1 MBC3, writing 00 actually selects bank 0, this is cleaner, sure. RAM banking up to 16 RAM banks, 128 kilobytes. RAM enable, no banking mode, no weird MBC1 style mode switching, no RTC, that's MBC3 only. Rumble variant, some MBC5 have a rumble motor. Bit 3 of the RAM bank register controls a motor on and off. The RAM bank is then the only bits 0 to 2. For emulation, you can just ignore the rumble bit. Yep. So implementation difficulty, easiest MBC to implement, no quirks, no special registers, clean banking, and here's a summary. Great. So what Pokemon needs? Pokemon Red Blue, MBC3, some cards, or MBC5, later prints. Pokemon Gold, Silver, Crystal, MBC3 with RTC and battery. I'd suggest implementing this order. MBC3 needed for Pokemon, moderate complexity. RTC is an interesting part. MBC5, easiest, covers most games. MBC2, low priority, few games use it. Along with MBC3, we'd also want to implement cartridge RAM, okay, and battery saves. Since Pokemon needs both, want me to start planning implementation? Yeah, let's just start with MBC3 first. Let's hold off cart RAM and battery saves. Let's hold off battery saves. Wait, no, you kind of have to do. Okay, let's just start with MBC3 first. Let's just start with MBC3 first. Yeah. Okay. So, and also since we've already committed, we have like a fresh change set, so we can just follow along the implementation. Okay. Yeah. I expect it to be not too much code. I think the RTC doesn't sound as bad since we're using our system clock to just update the appropriate register. So again, all this is just kind of like memory, right? So as long as we write to those addresses and read to those addresses with the right values and probably implement that latching to return the snapshot of the time. I think that's all what the RTC really is in terms of software. Okay, so I'll let this run. Okay, it's interesting. I had doubts on the battery saves too, and like I was wondering if this could be a separate task, and I think it should, because I do want to learn how that works. So yeah, let's defer. Let's just do the MBC3 banking, RAM, and RTC, and then let's do a save file persistent as a follow up. Let's just try to get it right. Okay. So here's the plan. Ooh, this looks big. Okay. So architecture, MBC strategy pattern. So we're gonna create something, I guess, reusable now. Okay, so here's the thought. Okay, so the emulator has MBC0, ROM only, and MBC1 work. To run Pokemon, we need MBC3, which adds 7-bit ROM banking, cartridge RAM, and optional real-time clock. The current cartridge class has all the MBC logic in a single write method with hard-coded MBC1 behavior. This won't scale, so we'll refactor to a strategy pattern where each MPC type is its own class. Makes sense. Okay, then we'll just probably inject the specific one when we're creating a cartridge. So the MPC strategy pattern. The cartridge class keeps header parsing, checksum, print header, and ROM data ownership, and use self MPC attribute points into a small strategy object. No MPC, MPC1 or MPC3 that handles banking logic, cartridge RAM, and RTC. The cartridge read and write methods simply delegate to self MPC. This matches the existing codebase pattern where memory delegates I/O to subsystem objects. Timer, serial, joypad, PPU. Implementation. You create source, cartridge, MPC Pi, MPC strategy classes, 3 classes with read address, okay, and write. So that's the base interface. No MPC, ROM only. So flat ROM access, no banking, no RAM, writes are ignored. It's ROM, so that's why. MPC1, exact replication of the current behavior, sure. MPC3, all these features, which we already discussed. So we're just going to modify gb-cartridge.py. We're going to implement no MPC, MPC1, MPC3 from the MPC cartridge package. Then we're here in init MPC. We're going to create the instances. And then we're just going to forward all the reads and writes to the appropriate MPC. And then we're going to have to expand the address range to include 0x8000 and 0xBFFFF for cartridge RAM because MPC 3, 5, and 2 have cartridge RAM. Add backward compat properties, RAM bank, RAM enabled, banking mode that proxy to self MPC, so existing MPC1 tests keep working unchanged. And modify GB memory for external RAM dispatch. Add cartridge dispatch for 0x8000 to 0xBFFF and both get value, set value. Sure. So then when no cartridge is loaded, falls through internal memory array, preserves existing behavior. Okay, so when no cartridge is loaded and somehow, memory writes are happening, you're just going to write directly to RAM. Okay, so synthetic ROM builder. What is this? Oh, it just creates like a ROM that tells you that, okay, this is MPC3 and stuff like that. So kind of like a mock ROM. Okay, yeah, let's auto accept edit. I do not want to clear the context. Let's do it. Okay, so we're done with the basic MPC3 implementation. So let's take a look at the strategy pattern that was implemented because I think it's quite interesting. All right, so we have a source cartridge.mbc. So there's going to be 3 types of classes here. Okay, so if we go to mbc.py, you'll notice that no MPC just directly reads and writes to those banks. So that's easy. And notice how every one of them have the same kind of like method signatures, just read and write. So this MPC1 was already taken from the original implementation, but this one here, MPC3, is going to be the one that's new. And it initializes with ROM data, num ROM banks, RAM size, and has RTC. Whereas this one initializes with everything else except for has RTC. And if there is RTC, we are going to set up an internal instance variable of RTC registers. There's 5 of them, and we'll have latch state, halt base timestamp, and base seconds. And it's just really just keeping track of time. So in this case, we'll just start with base timestamp of our system time. So in base seconds, it's going to be 0. And then at some point here, we're going to try to read from RTC. And so reading from RTC is going to be, I think this one, right? So that's how we're going to read. And we're going to write. So all these other addresses too. But basically, oh, here we go. Yeah, latching RTC gives us like a snapshot. So we're going to freeze. So RTC halted. If RTC halted, we'll get total equals base seconds. Sure. and then else, we're gonna just kind of tick, and then we're gonna take that total that we just got, and we're gonna kind of like decompose that into seconds, minutes, days, hours, and then we're just gonna reassign it, okay, and then we're gonna return back, or at least write back to, the right values all in these registers, and then write to RTC registers. So write to an RTC register, update internal timekeeping. Let's see. Again, at some point we're going to take from system time somewhere here. Okay, yeah, here and here. We'll have to compute all these values and update them. Sure. I think if I were to sit down, I can like really trace all this, but let's move. Okay, so what has changed here in GB cartridge is right here. So this one just initializes the right MBC instance. Okay, and if I guess if this one has RTC, you're going to start RTC anyway. And then this one just kind of includes this new range of addresses, external RAM. And all these RADs are just being pulled to MBC1 in this case. So it becomes cleaner. So self MBC write and self MBC read. It just becomes a lot cleaner. GB memory is just going to do directly. So now this is the external RAM. So you want to just like read address, same thing. The cartridge will handle it as appropriate. And that's it. So yeah, commit and push, and let's see if I can at least load Pokemon Red. Then we can focus on battery saves, because I think for Pokemon you're not really required to have the battery save to work. It just won't save. So let's see. In this case now, okay, so let me try loading, see what happens. We can check the header and run, okay. For a bit without the GUI. Handler loads fine. Let me try running it for a few frames to see if it crashes or gets anywhere. It should, I mean, at this point, it runs without crashing, yeah. Pokemon Red does a lot of setup before turning the screen on. Let me run it longer. I mean, the base CPU and PPU are working, so if anything, it's just any problems with MBC and how it's reading and writing to and from memory. So if anything, it's wrong on the MBC, and it looks like it's correct based off of this ASCII art here. Okay, so Pokemon loads and run. The screen is showing scrolling intro sequence. Okay. Yeah, let's just run it and see what happens. Oops. No, not this one. Scale equals 5. Let's do that. Okay. So this takes a while, but we have Pokemon, at least Pokemon Red, working. Is it decently fast? Yeah, look. Okay, we're getting the right frames per second. So this is good. Yeah, we have Pokemon running. Cool. So with the green screen. But I think eventually we'll figure out how to implement that Super Game Boy Color palette. See, so I can just hit start and just go right onto it. There's no sound yet, but we have red version. This is good so far. Okay, let's see if we can just start a new game. Oh, did I just hit B? Sorry. Let's do it again. Okay. Come on. New game. There we go. There we go. So here's Professor Oak, and I think you're kind of familiar with, hello there, welcome to the world of Pokemon. My name is Oak. People call me the Pokemon Professor. Right? And is it this world is inhabited by creatures called Pokemon? Okay. For some people, Pokemon are pets. Others use them for fights. Myself, I study Pokemon as a profession. Cool. First, what is your name? I will call myself. Red. Okay. Right. So your name is Red. Okay. Let's see how hard this computer's working. Oh, not too bad. Okay. So this is my grandson. He's been. Come on. He's been what? Oh, I'm not even focused. He's been your rival since you were a baby. What is his name again? It is Blue. Okay, that's right. I remember now. His name is Blue. Okay, Red. Your very own Pokemon legend is about to unfold. A world of dreams and adventures with Pokemon awaits. Let's go! Okay, so I'm gonna see if I can move around a little bit, and then I think that's good for the test, and then we'll implement battery saves. Yeah. So yep, here we go. We're good. We have implemented Pokemon. So at some point, let's see here. We have dialogue too. Yeah. Mom, right? All boys leave home someday. It said so on TV. Professor Oak next door is looking for you. Okay, enough. All right. So let's commit and push, and then uh do battery saves. Okay. We already did commit and push, did we? Yeah, we did. Okay. So it works well on Pygame. Let's move to battery saves. Is it just dumping memory bytes into a file? It is, right? It's just a range of addresses into it. Okay, so I think once we do that, I'm just gonna stop recording. We can test it some other time. But we made a lot of progress. Uh, mm, let's see. Okay, so yes, essentially here's how it works. What battery saves are. The cartridge has a small RAM chip. For Pokemon Red, it's 32 kilobytes. 4 banks of 8 kilobytes. A coin cell battery and a cartridge keeps this RAM powered when the Game Boy is saved or is off. Your saved game lives entirely in this RAM. What we need to do on shutdown, dump the cartridge RAM byte array to a save file. Just raw bytes, no header or format. For Pokemon Red, that's exactly 32K. On startup, if a save file exists next to the ROM, load it back into the cartridge RAM byte array. That's it. The save file is literally just open path, blah, 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 right, self.ram. Yeah, that's true. Every emulator uses the same format, so it's just an image of the RAM, a raw dump of cartridge RAM. So save files are interchangeable between emulators. Where to hook it? Yeah, sure. Yeah, yeah, but I also want the save file to be dumped if I hit Control C on the terminal. So most likely we need a sig kill handler. Yeah, because I want to make sure that, even though I Control C or whatever, it's like it still flushes out the save file. And the reason why you don't want to like you might ask, okay, why don't you just dump the save file when you hit save on the game, right? It doesn't know that, right? Because like your ROM is doing all these things, but your emulator has no idea. Your emulator is just a game runner. That's all it is. So yeah, exactly right. Sig kill is uncatchable, but Control C is just a keyboard interrupt when try finally handles clean. Okay, so yeah, it'll implement that. Sig kill. Oh, it's yeah. Never mind. But sig in Control C. Yeah, that's what I was talking about. Yeah. So we'll do that. It's quite easy actually. Just do an OS writes. Where is it? Right here. OS Save the cartridge RAM to a save file. F.write RAM. Open self-save path. Write binary. Okay. Try finally. So finally is going to always execute. Okay. I hope you guys don't mind. I'm just gonna test it one more time, and then see if it works. And I might tell it to change the color palette. The green is a little too harsh for me, but we can save that for another day. I'm not that retro. Okay. Okay. Cool. Let's play. Okay, so let's try this again, but let's just, I don't know how we can hurry it up. So we can like, yes. By the way, any way we can implement something to speed the game up, like how some emulators do it? Okay. Okay, yeah, it's simple. So just skip time sleep throttle. Right now, the emulator runs 1 frame, renders, and so that we skip the sleep. It runs as fast as CPU can go. Most emulators bind to this hold to fast forward key. We could hold space, skip sleep, uncap speed, release space back to normal. One line change the main loop. Well, not uncap, but more like 3x. Yeah. Yeah, that's fine. I'm okay with that. Let's do it. So we can hold space to do that. So uh, let's see. And I think we should have. Do we have anything saved? Yeah, we have stuff saved. So, but then I don't think it's gonna be garbage for a cartridge. So okay, let's see. I'm gonna assume it works. So we hold space. Hold space. Speed. Is it speeding up? Let's see. Fast forward. Oh, you just hit it one time. Hold space to run at 3x speed. Release. Go back to normal. Sure. I'm holding space. Is it going? Let's see. I don't feel like it's going. I don't feel like it's working. Yeah, I don't feel like it's working. Holding space is not working. Let's see. Holding space doesn't seem to be doing anything. Yeah, I don't think it's doing anything. Running slower than real time. Ha ha! Okay. It's going to render the last one, so let's see. And it does mean that our computer is too slow to run the simulator at full speed. But I guess that's okay. What is it doing? Okay, the issue is that rendering whatever is the bottleneck. Each framework took longer. Ha! Okay, let's do it again. Does it work now? Come on. Yeah, it feels like it's working. I guess it's just the nature. It's just slow. So let's see. Okay. Yeah, the computer is just slow. Okay, fine. So yeah, so it's just my computer being a bit slower. That's fine. I'll be patient. Okay. Okay, so yeah, just rendering is slow. Um, maybe if I just reduce the window, but I want to like be able to show all this, you know? So I'm just gonna keep going, and then once we can validate a save, I think we can be good. I wonder, I can't remember if we have a save game, can we skip this intro? So, was it red? Okay. Yeah, I thought it was fast, but this is actually pretty slow. Well, that's another problem for another day. Um, okay, let's go with, in this case, it's gonna be blue. Okay, cool. So, Pokemon Journey is about to begin. Come on. Okay. Alright, moment truth. Let's save. So, we're gonna just start here. We're gonna save the game. Okay, let's see if we can save. Would you like to save the game? Yes. Okay, now saving. Are we gonna crash? Are we gonna stable? We're gonna be stable? Yeah. Okay. Time should be like a few minutes, right? So, save. No. No, let's not save the game. Okay, now, technically, if we quit right now, we still end up back around here. So let's quit. Okay, now, let's, go back and start the game. This time I'm going to scale at 3. Just maybe it'll be faster. Yeah, it does feel faster now. I'll just be greedy in my high resolution screen. Yeah, it does feel a lot faster, so it's like, yep, it's smoother. Okay, well, let's see. So I skip all that. Now, can we load? Oh, continue. There we go. Okay, so continue. Let's see. Let's see. Yeah, look at that. We can continue. We have saves. Yay, it works. Okay, great. Okay. Okay, everything saves correctly. Let's stop here and continue next time. Update progress with agents.md. Okay. I think that's it. So I'm just gonna update agents.md, commit and push, and next time let's work on do we care about sound? I don't know. Let's just do it for fun. Let's do it for fun, and then we'll implement like a screenshot like tool thing, and then let's also implement like the HTTP server soon. So I think the sound shouldn't take too long. It's just a bunch of like square waves, I think. All right, so see y'all next time.